In this video, we're going to learn another test that would help us determine whether my series is convergent or divergent, and it's the comparison test. So we have two types, either a comparison test by itself, comparing series separately, or we have the limit comparison test where we use a limit to help us identify whether the series is convergent or divergent. So let's start with the comparison test. So the comparison test is where we have a smaller series, a smaller sequence, and a bigger sequence. So to determine whether a series is convergent or divergent, I can compare it with a series that I already know. So for example, I already know that the harmonic series, which is the summation of 1 over n, is divergent. So I might be able to use it to identify whether another series is divergent or convergent. So let's see what the theorem tells us. If the bigger series, which is the summation of p of n, converges, then the smaller series definitely converges. And if the smaller and if the bigger series diverges after a certain value n, this means that my smaller series also diverges. We also know that if a smaller series diverges, then the bigger series definitely diverges. Okay, so that's a lot of convergence and divergence. So let's see how we're actually going to use it. If we have the summation of 1 over n minus 1, I'm going to compare it with the harmonic series, which is 1 over n, which we already know that diverges. So now, if we make the denominator smaller, this means that my fraction becomes bigger. So now if I make it smaller by subtracting 1, this means that this series here, or this fraction, is bigger. So now by the comparison test, if a smaller series diverges, then the bigger series also diverges. That's it. Let's try it with the next example. But for this example, I want to compare it with the summation of 1 over n squared. Now, this series, I already know that it converges using the p-series test because p is equal to 2, which is bigger than 1, which means it converges. Now again, if I make my denominator bigger, this means my fraction is smaller. So here, since n is positive, if I'm adding to my n squared something positive, this means my denominator is bigger now. So the fraction is smaller. So now using the comparison test, since the bigger series is convergent, then the smaller series also converges. That's it. So the comparison test is all about using the facts that I already know, whether it's like a p-series test or a harmonic series, a geometric series that I already know some facts about, and I already know how to determine whether they diverge or converge, and compare them with something that I don't know anything about. So for example, this, I don't know anything about it directly, but if I compare it with something that I already know facts about, using the comparison test, I can determine whether it converges or diverges. Okay, how about this example? This series looks complicated. Like, how would I know whether it converges or diverges? Using the things that we've already learned, there is nothing that I can use directly. But let's think about it. I can compare it with something that I know that converges or diverges. So now let's look here. My numerator is n. I can't take it out because if I take it out, this makes it smaller. And I want something that's going to be bigger. So now we know that if I make the denominator smaller, this means that my fraction becomes bigger. So now we want to be smart about it. I want to take things out that would help me simplify my fraction. So if I take 1 by itself, I'm going to still have n cubed plus n. If you take it as a common factor, you're going to have n squared plus 1. So here, although this kind of worked, but I don't know something that's going to give me a convergence or divergence directly. But if I don't have the 1 here, if I have 1 over n squared, I know that this series converges. So a smarter choice here is, instead of just taking the 1, let's take the n2. So let's remove n plus 1. This is positive. If I take it out, my inequality is still correct. Now I made my denominator smaller, so my fraction became bigger. So here, once you simplify, you're going to get 1 over n squared. Now this thing here, if I take the infinite series off, I know by the p-series test, this converges. Now by the comparison test, if the bigger series converges, then my smaller series also converges. So this series is also convergent. So that's it. It's all about using the facts that we know, comparing with things that we don't know, and kind of relate things together. Now the limit comparison test tells us that if I have two sequences where I take the limit for, if I take the limit of an over bn, and the value of it is any number that's not 0, then either both of the series convergent or both of them divergent. So here we're going to use a fact where, like, oh, I already know that bn converges. So if my limit for an over bn is not 0, then the summation of an also converges, and so on. If the limit of an over bn is 0 and the summation of bn converges, then this proves that summation of an converges. And if the limit is infinity and summation of bn diverges, then the summation of an diverges too. Now, if I have the limit to be equal to 0 and the summation of bn diverges, then I don't know anything about the summation of an. And if the limit goes to infinity and the summation of bn converges, then this test does not provide any information about the summation of an. So it's only these conditions that work with the limit comparison test. So now let's use this test to determine whether this sequence converges or diverges. So here we want to be able to choose something that's going to help us find the limit, and at the same exact time being able to use the limit comparison test to find the value. So here, let's use something that we already know. Since I have 1 over n squared minus 1, let's use something that looks kind of similar to it, but we know something about. So I know that this series converges, so I'm going to use it. So if I want to use the limit comparison test, let's take the limit. So I'm going to do an over bn, so that's 1 over n squared minus 1 over 1 over n squared. So now if you do the keep change flip rule, you're going to get the limit of n squared over n squared minus 1 as n goes to infinity. If you use L'Hopital's, you're going to get 1. Now since this limit is not equal to 0, and using the first part of the theorem, since the limit is not equal to 0, and I already know that this summation is convergent, then the summation of an, which is the summation of 1 over n squared minus 1, also converges by limit comparison test. Now let's look at this example. Let's compare this with something that I already know, something that would be helpful. So how about I take 5 over 3 to the n. Now this is a geometric series, and I know that for a geometric series with r equals 5 over 3, since this is bigger than 1, then the series diverges. Okay, so let's see. Limit comparison test, I need to take the limit of an over bn. So if we do that, now we can cancel 5 to the n, and if we do the keep change flip rule, we're going to get this. Now this limit equals 2. 1, which is not equal to 0. Now again, using rule number 1, if the limit is not equal to 0, and I already know that the summation of Bn diverges, then the summation of the thing that we know that we want, like the summation of An, must be the same. So if this diverges, then this diverges using the limit comparison test. So here it's all about choosing the B of n. Now you need to choose B of n to be something that you already know facts about. I already know that this series converges. I already know that this series diverges, and this choice would help me cancel things out. So here I chose 5/3, so I can cancel 5/3 somehow here, and so on. So this is it for the comparison test. You can do these problems from the book if you want extra practice, and if you go to Lumen Homework 4, you can do problems from 10 to 13. Let me know if you have any questions, and best of luck.